Good morning.
Morning, Jennifer.
I have to pop out early today. Is there a way I can view today's Zoom meeting later?
Yes, I will see if I can put it on YouTube and put a link.
Okay, that'd be great. I have an appointment in the valley, so I have to leave.
Okay. Did you have any questions?
No, so far so good.
All right. All right. Well, looks like there is one of you today. Two of you. Good morning. So we're going to start with 3 molecules, and we're going to figure out what kind of intermolecular attractions would result for each of these. So we'll start with hydrogen. How many valence electrons does hydrogen have? So we got to draw its structure. Also a good review for the final. How many valence electrons does hydrogen have?
1.
All right, so we will put 1 dot around this hydrogen and another dot around that hydrogen. So you'll notice hydrogen is just a single bond between the 2 hydrogens. So what kind of intermolecular force would occur between 2 hydrogen molecules? So our choices are London dispersion, dipole, dipole, or hydrogen bonding. So what do you think for hydrogen?
London dispersion.
Right, because there is no dipole, because hydrogen would have the same electronegativity as the other hydrogen, so the electronegativity difference would be 0. So this one would be London dispersion. All right, let's draw CH3Cl. How many valence electrons does carbon have? Right, so carbon has 4 valence electrons. So if I put 3 hydrogens around it, and then how many valence electrons does chlorine have?
Two.
So chlorine's here. So just count from the left.
7.
All right, so chlorine would have 7 valence electrons. So it needs one more, so it can single bond with the carbon. So we would have carbon with 3 hydrogens and 1 single bond to a chlorine with 6 non-bonding electrons. So let's say we have another CH3 chlorine group. What is the intermolecular attraction between these two? So is there a dipole between carbon and chlorine? Well, we need to know the electronegativity of carbon and the electronegativity of chlorine. Looking on this periodic table, the electronegativity value is right below the crystal structure. So for zinc, it's 1.65. So for carbon,
I can't see the paper.
you can't see the paper.
No,
What do you see?
I don't like see your screen I shared.
All right. That help?
Yes,
So carbon's electronegativity is on this chart 2.55. Chlorine's electronegativity is 3.16. So 2.55, 3.16 for chlorine. So is there electronegativity difference greater than 0.35 between carbon and chlorine? Is the difference between those two numbers greater than the 0.4 that we talked about yesterday?
Yes.
All right, so which is going to be the negative one, the carbon or the chlorine?
Is it the chlorine?
All right, chlorine is the higher number, so it's going to be the negative one. Carbon is a smaller number, so it is the positive one. So then we can look at it over here also. Carbon is the positive, chlorine is the negative. So now we have the attraction between this carbon and this chlorine on 2 different molecules. So what kind of intermolecular attraction is that one? London dispersion, dipole-dipole, or hydrogen bonding? Is there a dipole on this molecule between the carbon and the chlorine?
Yes.
All right, because carbon's positive, chlorine's negative, so this one has a dipole. And same molecule, so this one must also have a dipole. So this one is dipole-dipole and London dispersion. Because everything has London dispersion. So the hydrogen molecule was only London dispersion. This molecule is both dipole-dipole and London dispersion. Then let's look at carbon monoxide, CO. So carbon has 4 valence electrons. Oxygen has 6. So we're going to have a triple bond between the carbon and the oxygen. And then let's look at another one. So we know the electronegativity of carbon was 2.55. And let's see what oxygen is. Like it is 3.44, or if you have your little electronegativity chart, it might be slightly different, but it should be pretty close. So is there a dipole between the carbon and the oxygen?
Yes.
Okay, so if this one has a dipole, it's the same molecule, so this one must also have a dipole. So this one is dipole-dipole. And of course, everything is also London dispersion. Now, do any of these three have hydrogen bonding?
No.
Good. Even though this is a hydrogen, between two hydrogens is not hydrogen bonding. Between a chlorine and a carbon is not hydrogen bonding. And between a carbon and an oxygen is not hydrogen bonding. And our last one is water. So oxygen has 6 valence electrons, hydrogen has 1. So there's a water. And we can have another water. We know the electronegativity for hydrogen was, did we calculate it? Nope. So oxygen is 3.44. Hydrogen is 2.18. So is there a dipole between the oxygen and the hydrogen?
Yes.
So which one is the negative, which is the positive?
Oxygen's positive, hydrogen's negative.
Just backwards. So the higher, these are electronegativity values. So the higher the number, the more negative it's going to be. So the oxygen would be the negative one. Hydrogen would be the positive. So the higher the number, the more negative. And then this hydrogen over here is positive. This oxygen is negative. So the attractive force between the two water molecules. Does this one have a dipole? Is there a difference greater than 0.4 between oxygen and hydrogen?
Yes.
So this one has a dipole, which means this one also has a dipole. And then of course it has London dispersion. The other question, does it have hydrogen bonding? So,
No.
so what do we need for hydrogen bonding? We need a hydrogen, right? And what does the hydrogen have to be attached to?
Oxygen or fluorine?
Oxygen, fluorine, or one other one,
Nitrogen.
nitrogen. So let's look, do we have a hydrogen attached to an oxygen, nitrogen, or fluorine in our water? So you have hydrogen attached to an oxygen in the water molecule.
Yes.
All right, so that part is true. Now, the hydrogen has to be attracted to either an oxygen, or sorry, a fluorine, an oxygen, or a nitrogen. So is the hydrogen that's on this water molecule attracted to a fluorine, oxygen, or nitrogen on the other molecule? So is this hydrogen, is it attached to a fluorine, nitrogen, or oxygen?
Oxygen.
So this part was true, this part is true. So this is a hydrogen bond. So this one would also have hydrogen bonding. Now, the strongest of the three is hydrogen bonding because it's a very strong dipole-dipole. Then dipole-dipole, London dispersion is the weakest of the forces. So looking at this problem right here, which of these molecules had hydrogen bonding, dipole-dipole, and dispersion? So which of those molecules had hydrogen bonding, London dispersion, and dipole-dipole? Isa? Isabel?
The water molecule.
Right, the water molecule has all three. Then you'll notice the carbon monoxide had dipole-dipole and London. The CH3Cl had dipole-dipole in London. And the hydrogen molecule only had London dispersion. So if I'm doing question 5 on my homework, the water had all three. The CH3Cl had dipole and dispersion. The carbon monoxide had dipole and dispersion. And the hydrogen only had dispersion. All right, next one we're going to look at is a flask contains 0.663 grams of water at 22 degrees Celsius. The vapor pressure is 19.8 torr. What is the minimum volume of the flask so there is no liquid water in the flask? So this one looks like a gas law problem. So when we have gases, we have PV, N, R, and T. So do I know any of those pieces?
I don't know any of this. In Mexico.
So we have T as 22 degrees Celsius,
Great.
and the pressure is 19.8 torr. And then R is a set value.
She hit me. Good job.
How about volume?
That's what we're looking for.
And how about moles then? We need moles. Or do we have anything that's close to moles?
That'd be 0.663 grams.
All right, 0.663 grams.
Wait, what?
So I know pressure. 19.8 torr. Volume don't know. And this is for water. So how do I change 0.663 grams of water into moles of water?
Take the mole bus.
All right, so how do I do it? How do I change grams into moles?
Find the molar mass.
All right. What is the mass of hydrogen?
1.
And oxygen?
16.
What was that again?
16.
All right, so I have 2 hydrogens and 1 oxygen, so 16 plus 1 is 18. So 1 mole of water over 18 grams of water. So our grams cancel. That leaves us in moles. So 0.663 divided by 18.
.0368.
All right, so now I have pressure, moles, temperature. What do I have to do with temperature?
Change it to Kelvin.
How do I do that?
Add 273.
So that would be 295 Kelvin. And what is R? Anybody remember R? 0.082057 liters atmospheres per Kelvin mole, or 62.36 liters torr per Kelvin mole. So to change liters atmospheres into liter torr, we just multiply by 760 because there's 760 torr in 1 atmosphere. So then we use our equation, PV equals nRT. How do I solve that equation for volume?
nRT divided by P.
All right, so divide both sides by P. Now I'm in volume. So volume equals the moles, 0.0368 moles, times the gas law constant, 62.36 liters torr per Kelvin mole, times the temperature, which was 295 Kelvin, all divided by the pressure, which was 19.8 torr. So we have 0.0368 times 62.36 times 295 divided by 19.8. Looks like 34.19, rounded to 3 significant digits, 34.2 liters. So that's the volume that we would need to keep it from turning into a liquid. So this is simply a gas law problem. Any questions on that one? So this went back a couple of chapters. So we had to incorporate what we learned a couple of chapters ago in this chapter. So this chapter incorporates a lot of different chapters. So questions? So questions 10 and 11 on your homework both involve this kind of a problem. This was 34.2. All right, here is our heating curve. So tell me what pieces go where? What goes in the bottom left?
Solid and liquid.
What goes in this flat area?
Liquid only.
What would go as we're heating it up?
Liquid and gas.
This section?
Gas only. So I guess the first one would be solid only. And then move everything up one.
So this is only a gas when we've heated it to steam.
And it's, yeah, when it's vaporized.
So when it's boiling, you have both liquid and gas, because it's starting as a liquid, turning into a gas, so that transition has both liquids and gases.
Yeah, I was thinking the solid and liquid in the beginning for the ice melting.
So as the ice heats up to the melting point, it's still a solid. When it reaches the melting point, then when it starts to melt, you've got some solid, some liquid, just like leaving your piece of ice on the table. You've got some solid ice, you've got some liquid. After it's all melted, it's all liquid. And then when you heat it up, like you're boiling water on a pan, you still have water, and then you see the steam coming up, that's the gas, so you have both. And then pretty soon all the water is gone out of the pan, which means it's all gas at that point. All right, very good. All right, boiling point. So when the vapor pressure of a liquid increases enough to reach the, or to equal the external atmospheric pressure, then we call that the boiling point. So that's when the vapor pressure equals the atmospheric pressure. So the temperature that the liquid boils at depends on the pressure or the atmospheric pressure. So when we are at sea level, then water is going to boil at 100 degrees Celsius. And during that whole process, temperature of the water is going to stay constant. But if we go to a higher elevation, meaning less pressure, then the water is going to boil at a lower temperature because the pressure is lower. So high altitude, the atmospheric pressure is lower, so the boiling point is lower. So the lower the pressure, the lower the boiling point. So if you remember when we had our syringe and we reduced the pressure a lot by pulling out the plunger, we ended up boiling water at room temperature. So here's a little graph showing ethyl ether, ethyl alcohol, water, and ethylene glycol or antifreeze. So you'll notice the water, when you are at 101.3 kilopascals, which is 1 atmosphere, the boiling point of water is 100 degrees Celsius. But as the pressure goes down, the boiling point of the water goes down. So when you're at a pressure of 27 kilopascals, your water is going to boil at around 68 degrees Celsius. So you see, as you reduce the pressure, the temperature, the boiling temperature decreases. And that's true for any liquid that you have. And we're not going to worry about the Clapeyus equation. So here's our little graph that we just talked about, the heating curve, where we had solid, then the melting is the plateau region. Then we have liquid, and we have the boiling point, and then we have all gas. So this is just a heating curve. Now, phase diagram. So this is a phase diagram, or doesn't tell me what the compound is, but at a certain pressure and temperature, you either have a solid, a liquid, or a gas. So on the left side, you'll notice the purplish color, we're a solid. So if we're at fairly high pressure and we increase the temperature, it's going to go from a solid into a liquid. So that's melting, or we can go liquid back into a solid, which is freezing. If we continue to increase the temperature, then the liquid turns into a gas. That's vaporization, or if it condenses back, gas to a liquid, that's condensation. Now, if you look at the very bottom part of the graph, at very low pressure, we're a solid, it can go straight from the solid into a gas, which is called sublimation. My wife actually just purchased a sublimation printer, which allows her to print something on a piece of paper. Then she puts that piece of paper around, either on a t-shirt or around a cup. Then she puts it in a convection oven, heats it up, and the ink sublimes, goes straight from the solid ink into the gas, and goes right into the t-shirt or right into the cup. And now she has a t-shirt with that image that she had printed out. And there was no liquid involved at all. So it's called a sublimation printer because the liquid ink turned straight into a gas, which allowed it to go into the porous cup or into the t-shirt. All right, here is a diagram for water. Triple point is where something exists as a solid, liquid, and a gas all at the same time. So at 0.6 at kilopascals and 0.1 to 0.01 degrees Celsius, H2O will be a solid, a liquid, and a gas all at the same time. Now, if we're at 101 kilopascals and we increase the temperature, we're going to go straight from a solid into a liquid. Let's say we are at 0 degrees Celsius. If I increase the pressure, you'll know we'll go from a gas, then it goes into a solid. And then if you continue to increase the pressure, the solid will turn into a liquid. So what would be the state of water if we're at 101 kilopascals and 50 degrees Celsius? What state would it be in?
Water.
Right, good. All right, here's a phase diagram. I think this is question 18, 17, 18, somewhere in there. So here's a phase diagram for carbon dioxide. So it's 72 atmospheres, 0 degrees Celsius. So 0 Celsius, 72 atmospheres. What is going to be the state or the phase of carbon dioxide? Solid, liquid, or gas? "72 atmospheres, 0 degrees Celsius." So you have to find those points on your graph.
Would it be solid?
All right.
Liquid.
Can you see my mouse at all?
Yes.
All right, so 72 atmospheres would be here at the top. So going over to 0 degrees Celsius. So here the red mark is around negative 56. So keep going. 0 is probably going to be somewhere around here. So you're right, it would be a liquid at that pressure and temperature. So starting at the same point, 72 atmospheres, 0 degrees Celsius. What change would result if we decreased the pressure?
It might turn into a gas.
Right, so liquid into a gas, is that vaporization, condensation, sublimation, freezing, melting, or deposition?
Vaporization.
All right, very good. What if it went from a liquid to a solid? What would it be? What do we call liquid to solid?
Freezing?
Yes. All right, so you should know all of these words: vaporization, liquid to gas; condensation, gas to liquid; sublimation, solid to gas; freezing, liquid to solid; melting, solid to liquid. What's deposition? The opposite of sublimation. So gas back into a solid. All right, questions so far?
Sorry, can you repeat the definition for deposition?
Deposition, so sublimation is solid to gas. Deposition is gas back to solid.
Okay, thank you.
So freezing and melting are opposite of each other. Boiling or vaporization and condensation are opposites, and sublimation and deposition go together.
Can we do question 11 together?
Sure, why not? Let me find question 11. All right, this one says air conditioners dry the air while they cool the air. Suppose an air conditioner is used to cool a room that is 7.16 meters by 11.08 meters by 2.46 meters when the outside temperature is 36 degrees Celsius. At this temperature, the vapor pressure of water is 37.7 torr. The partial pressure of water in the air is 85.5% of the vapor pressure of water. How much water in grams is removed from the air each time the air is cooled? Looks like a nice complicated question. So let's write down the information that we know. So it looks like a gas law problem because we're talking about air. So we have pressure, volume, moles, R, and T. So do I know any of those pieces?
You know, pressure and temperature.
Okay, what is the pressure?
37.7 torr.
All right, and the temperature.
28 Celsius. I'm sorry, that's my problem. Yours would be 33 Celsius plus 273.
So that would be 306 Kelvin. I know R, since we're in torr, 62.36 liter torr per Kelvin mole. Do I know the number of moles? Oh, that's what it asks. How many grams? So N is the question mark. Do I know the volume?
You have dimensions.
Yeah, so this is a cube. So how do I find the volume of a cube? This is your geometry lesson. You remember how to find the volume of a cube?
Length times width times height, right?
Yes, length times width times height. And we know the length, we know the width, and we know the height of this problem. So 7.16 meters by 11.08 meters by 2.46 meters. So here is our information that we have so far. All right, so we want to calculate the volume for us.
One nine 5.16.
Say that again.
195.16.
195.16 cubic meters. So that's meters cubed. All right. And there are 1,000 liters in a cubic meter. So 195.16 cubic meters. There's 1 liter. Sorry, 1,000 liters in 1 cubic meter. In other words, a milliliter is a cubic centimeter. And so 1,000 liters is a cubic meter. So how many liters would I have? Like 195,000, if I round to 3 significant digits, liters. So my volume is 195,000 liters. Now it said something about 85%. Anybody remembers that in the question? Let's see, go back to the question. So air conditioner used to cool air. There's our volume, 33 degrees Celsius. Pressure is 37.7 torr. But the partial pressure of water in the air is 85.5% of the vapor pressure of the water. So the vapor pressure in the air is 85.5% of the vapor pressure of water. And we know the vapor pressure of water is 37.7 torr. So what is the partial pressure of the air? So to do that, I would need to take 85.5% of my pressure. So the pressure is 37.7 torr. And I need 85% or 0.855 or 85.5 over 100. That will give me the pressure of the air. So 37.7 times 0.855. So 32.23 torr. So now I have all the information I need for my problem. PV equals nRT. Do you want to put numbers in or do you want to solve for n?
Solve the equation, then plug it in.
Okay, how do I solve for n?
Divide out by RT.
Good. So N equals the pressure, which was 32.23 torr. Times the volume, which was 195,000 liters. Divided by R, which was 62.36 liter torr per Kelvin mole. Times the temperature, which was 306 Kelvin. And you notice our Kelvin cancels. Liters cancel, torr cancel, leaving us with moles. So we have 32.23 times 195,000 divided by 62.36 divided by 306. Looks like it's 329 moles. And then how do I change that to grams? Remember from our last problem,
Molar mass.
molar mass of water was 18 grams. So times 18 grams in 1 mole. So let's take in our answer. 329 times 18 looks like 5,928 grams of water. All right, did that work? So I'm sure all of you had different different numbers, but that is the process. So this one was a little more complicated because we had to find the volume from a cube and then realize that there's 1,000 liters in a cubic meter. Then we knew the percent of the pressure to find the pressure of the air or the water in the air. So we had to do 2 little conversions to get our PV and R and T. And then we just put it into our gas law equation. Does that make sense, Angelina?
Yeah, it did.
All right. Do you have other questions?
No, that was it.
All right.
Oh, I had a question.
Okay.
Do you think that on our next, what is planned for our next class day? Or not what is planned, I'm sorry, on one of our next class days this week before the final, could we possibly go through the test that was due yesterday?
Sure.
Thank you so much.
You bet. So the last 10 minutes, we're going to actually finish up this chapter. So this chapter will be over today. It's fairly short and there's only 20 questions on your homework. I know some of you have almost all of them done. So I encourage you to try and get through all of them tonight or tomorrow if possible. All right, so freeze-dried food like ice cream that the astronauts eat are dehydrated by sublimation. So that's pressures below the triple point of water. So that's how they freeze dry our ice cream for the astronauts. And also, if you think of glaciers, in Alaska, up north. If you think of all of the pressure that's pushing down from all of this ice, there's a lot of pressure. So when you get to the bottom of the ice, because of the high pressure, the solid has turned to liquid. So the bottom layer is actually liquid water, which allows the ice to kind of flow over the hard ground. So that's why your glaciers are actually flowing, because you have a layer of water at the bottom between the ground or the rocky ground and the ice. So that's due to the pressure of the ice causing it to turn into a liquid. And we talked about our phase diagram. All right, the last thing we need to look at is the solid state of matter. So solids, what do they look like? So on the left, we have a crystalline structure, whereas the far right is amorphous, which is more random placed solid molecules. Crystal is nice little organized structure. So silicon dioxide has a nice little organized structure on the left, but on the right, we have rapid cooling. You'll notice that it's more amorphous, so it's not the nice little structure it was on the left. So the left is more crystalline, the right is amorphous, so it's more random. So here's a picture of sodium chloride. So think of the sodium as, or which one is larger, sodium or chlorine? So here's our periodic table. Here's sodium on the left, chlorine on the right. Which is larger, sodium or chlorine? We get larger or smaller as we go left to right. Same energy
Sodium.
level. Go ahead, say that again.
Sodium.
Sodium larger or smaller?
Larger.
All right, so as we go across, because there's more protons, it pulls the electrons in tighter, so we get smaller going left to right. So looking at this structure here, the purple would be the sodiums, the green would be the chlorines. So you notice it's a nice little structure.
I think we had that in the beginning. I think that same crystalline structure with sodium chlorine.
Yes. So this one's copper, so it's just copper metal. And you'll notice it's got a nice little structure also similar to sodium chlorine, sodium chloride. And here's 4 different structures. We've got diamond, silicon dioxide, silicon carbide, and then graphite. You notice the graphite is like sheets of carbon placed on top of each other, which is why we use graphite in our pencils, because that layers slide off, which allows the layer to slide onto your paper, which allows you to print or to write. So here's carbon dioxide and iodine. So looking at their solid structures. Another picture of diamond and graphite. So graphite has the weaker attractions. Diamond, because it's more structured, is or a three-dimensional structure is stronger bond. So that's why you can cut diamond at the angles or at the lattice structures. You can cut it. Graphite just peels off. All right, so here's our last piece. So for a crystal structure, we have a unit cell. So every corner touches how many cubes? Looking at this one right in the middle, how many cubes does it touch?
Five.
So you've got, it's gonna touch the one on the left, one on the right, back left, so that would be 4. And then think of the same thing on top, another 4. So it's actually touching 8 different cubes. So we're out of time, so we're going to finish up with our lattice structures tomorrow, probably about 10 minutes. I think it's the last 2 questions on your homework. So we'll talk about the different types of crystal structures, and then we'll talk about your test that you just took, and then get ready for your last test. And then we can be ready for the final. So last questions before we leave.
Can we get a final study guide?
See if I can find something for that.
Thank you.
You bet.
Thank you.
We'll be in Globe tomorrow, so in person for those of you that can join us. All right, see you tomorrow. Unless anybody has questions.
I have a question, Dr. McBride.
Sure.
Can I get my test reopened? I've been sick with COVID and I just been in bed all day. And I forgot to do it last night.
Okay, sure. I will reopen it.
Okay, thank you.
Okay, you're welcome.
Bye-bye.
See ya.
I have a question also.
Sure.
I was working my ER shifts. They're 12-hour shifts from Wednesday to Saturday. So I didn't finish my test last night either.
All right. I will open yours up as well.
Thank you.
You're welcome. Need to quit working so much, huh? Those are long shifts.
Dr. McBride, I have a question.
Sure.
So for the chapter 9 homework, I didn't know how to do some of the problems.
All right.
And I was wondering, like some of them I did it the way that we did in class, and I'm not sure what I did wrong.
Okay, I can go back and see chapter 9. So did you take the test?
Yeah, I didn't know how to do 5 problems in the test.
Okay. Let's see, chapter 9. Okay, see the ones you missed on the homework was 19 and 20. Looks like you got all the others correct.
I
Let me see,
thought I had 3 more.
3 more. Yeah, it's only showing that you yeah, all the others you've got right. Some of them it took you a couple of tries, but you only missed question 19 and 20.
Because on mine, it's showing that I missed 5.
Let's see. So here's a screen I see. There's, and it showed you only missed 19 and 20. So you did 4 attempts on question 17, but you got it right at some point. So let's see. What question 19 and 20 were? Oh, looks like there's 27 questions. Sure why it's not. There we go. Okay. Scroll over. All right, so you missed 19, 20, 23, 25, and 26. 19, 20, 23, 25, and 26. So do you have time to look at those, or do you want to look at them tomorrow?
I tried doing it.
Like, do you have time to look at them right now, or do you want to look at it tomorrow? I'm not sure if you have class now or not.
I have time right now.
All right, so I wrote them down: 19, 20, 23, 25, and 26. So 19. So here it says you've got 2-gram sample of KCN. Dissolved in water in a calorimeter that has a heat capacity of 1.84. I thought I deleted that question. All right, so 1.84 kilojoules per Kelvin. Temperature, change in temperature was 0.270 Kelvin. You have to calculate the molar heat solution of KSCN.
So my problem says 3 grams.
All right. So yours says 3 grams.
Yeah, and then the total heat capacity is 2.09.
Kilojoules per Kelvin. And what was your change in temperature?
It was 0.240.
All right. So we have to find the change in enthalpy of the surroundings. So that's your calorimeter, which was 2.09 kilojoules per Kelvin. And we're going to multiply that by the change in temperature, which is 0.240 Kelvin. And that will give you the kilojoules for the surroundings. So let's see, 0.24 times 2.09 Looks like 0.5016 kilojoules. And then we have 2 grams of the KSCN. We need to change that to moles. So it's 1 mole over the potassium is 39.1. Sulfur is 32. Carbon is 12. Nitrogen is 14. Add those up. $97.1.
Zero point zero two.
0102.
No, 0.020.
0.020. That look right? We got 0.0206. All right, so then the change in heat of the solution is the surroundings absorbed 0.5016 kilojoules. And then we had 0.0206 moles. So that'll give us kilojoules per mole. Looks like 24.3 kilojoules per mole. So this was a little more complicated. So you had to take your calorimeter to figure out your surroundings by taking it times the change in temperature. And you had to change grams to moles, and then take your kilojoules divided by your moles.
You're on speakerphone and going down, okay, you got a student here. Okay.
So for the 3 grams, I got 16.898. That was my final answer.
Oh, right, that's right, because you had 3 grams. Okay. Okay. Sorry about that. I mixed the 2 questions up. I used 2 grams instead of 3.
Can we do the rest tomorrow because
Sure.
okay.
Yeah, we can do that.
Thank you for your help.
You're welcome. We'll see you tomorrow.
Bye. Have a good day.
You too.
Oh,